Very good evening to you, ladies and gentlemen. It is with great pleasure that I welcome you to this Geotechnical Forum organized by the Sri Lankan Geotechnical Society. Today we have Professor Thilakasiri talking to us on testing on piles. Few weeks back, Professor Saman did a presentation on optimization of the design of rock-socketed board and cast in situ piles. So this is a continuation of that actually. So Professor Saman is currently the Dean Faculty of Engineering of the Sri Lanka Institute of Information Technology and a senior professor in the Civil Engineering Department there. He graduated with first class honors from University of Moratuwa and obtained a master's with distinction from Imperial College London and a PhD from University of South Florida, USA. And he has been a fellow of the Institute of Engineers since 2007, and he has served in many academic positions at University of Moratuwa as Director of Postgraduate Studies, Director of Undergraduate Studies, and also in other universities in USA and UK. And he is a highly recognized consultant in the field of geotechnical engineering in Sri Lanka and overseas as well. So today he will be talking on testing of piles, which will be very useful to most of us. So without taking any further time, I will invite Professor Saman Thilakasiri to start his presentation. Over to you, Saman.
Thank you. Thank you, Atula. I'm audible, right? Can you hear me?
Yeah, yes.
Okay, thank you again. Now, today's my topic is actually testing of piles. So this topic is a vast area. So therefore, I will leave out the theoretical concepts and talk about only the practical side of the pile testing only. It will be a presentation having two parts. One is basically regarding the integrity of the piles. The other part is actually part 2 would be the testing of piles, load testing of piles using PD and other load testing mechanism. Basically, this is my presentation content. So the integrity testing, that is part 1. So PIT, CSL, cross-sonic logging. TIP is a new method, that is thermal integrity profiling method. That is part 2 will be load testing. So in that, these static load testing, instrumental pile load testing, and dynamic load testing using analysis using these two methods, and the final remarks. So this TIP, I will be very brief on that because that particular method is not being practiced in Sri Lanka yet. So with that, first one is actually the integrity testing of piles. So integrity testing of piles are required because the piles are not, in some cases, are integral. So earlier, actually, before 1990, right? So we were using coring through the piles, right? And determine whether there's a defect there. And so if the defect is nearby, to suspect it to be nearby the ground surface, then you would excavate and surrounding the pile and expose the defect. So those were the old methods that we used in the integral investigation of piles. So now with the invent of the non-destructive testing method, that is NDT, so we have different mechanisms to test the integrity of the piles. So one such method is surface reflection method. That is, you apply the wave or the sound wave at the surface of the pile and see the reflections. And then the direct transmission method, that is, so you embed tubes and you lower the probes in those tubes. So one will emit the wave, the other one will receive the wave, and you can look at the integrity between these two tubes. So, and the third method that is TIP, is actually a thermal integrity method, so which will avoid some of the shortcomings of the CSL as well, because CSL is not without any problems, but some of the shortcomings in the CSL method is also overcome using the thermal integrity profiling method. So these are the methods. So I will start with the surface reflection method. So the surface reflection method, that is, you apply actually the blow to the top of the pile, right? And you instrument the pile at the top, right? So this is a removable instrumentation, that is, you put a geophone or an accelerometer, and then you apply a small hammer blow to the pile, and then you can analyze the defects of the pile shaft. So when you do the analysis, you can carry out the analysis using two methods. That is a pulse echo method, that is what you call the PEM. The other one is transient dynamic response method, or TDR method, right? So when we analyze using the PEM, you basically do the time domain analysis, that what we do in most cases in Sri Lanka, even 95% of the time. And so when we do the TDR, we actually do the analysis in the frequency domain. So I will briefly touch on these two aspects. The other one is actually you drop a huge weight on the surface of the pile, and then you let the stress wave propagate through the pile and determine the integrity of the pile. So that I will not touch here in the integrity, because there will be a separate section. I will be discussing about the PDA method as well. So first I will look at the pulse echo method, and before we go into that, let me run a small video to show the method that we do, and then I will come back to this presentation. So this is basically the PDA test being done on a pile. What I would like to say is that you apply a small hammer and apply a small hammer blow, and there's an instrumentation that is through a geophone or an accelerometer, right? So you propagate a stress wave and then collect the information through this particular instrument, that is data collection, data acquisition system. So few points I would like to mention here. That is, the pile, actually you have to remove the basically the contaminated concrete, and come to a level where you have the actually the good quality concrete, and this is done right around the pile, looking at the integrity of the pile. So here we have the small accelerometer we install, and that can be removed, and also we apply a small hammer blow. And so data is collected here. You can see the data collected later. So let me stop this video. So we were here in this particular slide. So what we do is actually we apply a small hammer blow as you saw, and so then the data is collected, and there's a different type where the hammer is also instrumented. So this particular hammer is not instrumented, what we used there, because it is analyzed using the time domain, right? So therefore basically you collect the velocity at the top of the pile using the geophone and accelerometer with the time. So that is all that you do, and you apply about 6 flows at a particular location and travel right around the pile and also at the center. So if it is a pile without any defect, so what will happen is the stress wave will go down to the top, top of the pile and will come back. So until it is coming back, so there is no reflection that is recorded in the accelerometer. So if the initial stress pulse will be recorded in the accelerometer or the geophone until you get the reflection from the top of the pile, you will not see any reflection recorded in the accelerometer. So if it is a defect-free pile. So now these are the instruments we use there in the PIT, and you can see the small hammers. So there are different types of hammers here, different weights of hammers, and these hammers are not instrumented. But what is on the right, actually what is on the left, is actually instrumented with the load cell. You can see, and this can be connected to the data acquisition system. So the force applied through the hammer can also be measured, in addition to the normal PIT that we do for the pulse echo method. So now, if it is a file is defective, so you can see there's some kind of necking of the file. So there will be a reflection coming from this particular neck section, right? So I will run the video and see, run this. So you can see the stress wave is going down and it is coming to this particular section, right, where the defect is, and it is reflected back. And the other wave is actually the passing through the that defective section and will go to the top of the pile and will be returned back to the top as we normally do, right? So in addition to that, in addition to a defect-free pile, you can see there's a reflection created from the defect, right? So that will be recorded on the instrumentation at the top of the pile. So that recorded in this case, for example, that wave that is going back will be reflected and recorded in that particular instrumentation as a positive reflection, right? So sometimes that positive reflection, this particular stress wave that is going back and can also come back to the it can be reflected back or re-reflected, and then you can have a re-reflection of the original wave as well. So that is a possibility, right? So in both these cases, there's no skin friction here. Like in this case, of course, there's a little bit of skin friction, but in general, what we assume is that there's no deflection, no skin friction in the pile. So if it is skin friction less pile, then this is what will happen. So the interpretation of the PIT data is very simple if it is stop there. But what happens is that you will get a lot of complications. The first complication is that the stress wave that is you input at the top, you can see that it is a very small stress wave, and that will not go to the top of the pile. So that is one problem. So in that case, basically, if you basically that the toe is not investigated in this particular PIT. So that is basically what we call AB condition. That is, there's no toe reflection noted in this particular time domain graph. And the other one is the data is inconclusive. For example, there is sinusoidal wave that is created due to the reflection and re-reflection, and so basically you can actually have inconclusive data. You cannot interpret this kind of data that is there because you don't know whether this toe reflection or another reflection that is coming through, because you have multiple defects or multiple anomalies in the pile. So in that case, it becomes very difficult to do the interpretation. The other thing is that sometimes you can have increase in the impedance, and then you can have a reduction, and then so you can have a situation like this. So that is also very difficult to analyze, because you don't know exactly whether this is due to the increase in impedance and section coming back to normal, or it can be going to a section which is less than even normal. So that is that you don't know basically. So the situation becomes very complex in the actual scenario, not like what we demonstrated, what I demonstrated here, because there can be added complications. Now, for example, now here, now these three piles are from the same site, right? You can see pile 1, pile 2, pile 3. I have named them like that just to give you an idea. So these piles are from the same site, but one pile is actually longer than the other pile. And you can see the toe reflection of these piles. All these piles are actually kind of positive, right? So what is the positive toe reflection? Now, if you look at this one, you can see that the fixed condition or the fixity condition at the toe of the pile will generate kind of a negative velocity. But here, what we see is a positive velocity. So that means the pile is not properly fixed into the rock socket, right? So in such situations, for example, here you can see the toe reflection coming as a positive reflection, right? So all these three piles are showing that those positive reflections, and actually can have, for example, not properly fixed into the rock socket. That situation can happen. So if you look at all these three piles were subjected to PDA testing, that is load testing data. I will explain that. So, and the results of those are given here. Now, say if you consider pile 1, so diameter is 1.2 and skin friction is 1466. So if it is a 1200 millimeter diameter pile, so these are fairly small skin friction and rocks, very low end bearing for a rock socket pile. And pile 2 is giving, it is again 1.2 meter meter diameter pile, and you get the skin friction and end bearing like this. And pile 3 is a 1 meter diameter pile, and you can see it is giving fairly large skin friction and relatively higher end bearing. So if you consider the stiffness of the toe, so there's a way from the PDA you can get the stiffness of the toe. And you can see during the application of the dropping of the large weight, large hammer onto the pile, so it deflected. Settlement was in the range of 10 millimeters for pile 1 and 4 millimeters for pile 2 and about 2 millimeters for pile 3, right? And so if you calculate the relative stiffness of the toe, so these are the values, and you can see the stiffness of the toe, the pile number 3 is about 3 to 4 times, actually about 4 times the other piles. So, and if you consider this, these 3 piles, all these 3 piles showed actually the soft toe condition, but in the PIT, but actually the pile number 3 passed the testing because it shows relatively low permanent settlement during the testing, and also it has a little bit higher stiffness. So the higher stiffness in the sense that it is proper, it is somewhat better socketed into the bedrock, right? So by looking at the PIT, you cannot say whether the pile is okay or not. In that case, you can only actually suspect that pile is not okay. Maybe you have to subject that those piles to the further testing and see whether it is acceptable or not. So this PIT method is fairly good to identify the defective piles, right? So if there's a defect in the shaft, that will be shown, and if there's a defect in the toe, that will be shown. So if for example that is subjected to the condition that the reflection, the stress wave actually travels to the toe. So if it does not travel, then this method is maybe somewhat not useful. But this is kind of up to the wave penetration. You can actually you can interpret the results and see whether the pile is integral or not. So that is basically so the steps in the pulse echo method, that is the time domain analysis. So that is basically observe the velocity versus time record and identify the velocity pulse corresponding to the pile toe. So if it is not detected, then we have a problem. A reflection corresponding to a wave velocity in the range of about 3,400 meters per second to 4,300 meters per second may be identified as a toe reflection. Toe reflection is further verified by comparing the wave velocity of the piles from the same side. So you can see the wave velocities of the piles from the same side and see whether, because we get the concrete from the same supplier, and the wave velocity depends on the strength of concrete. So the piles from the same side should have approximately about the same wave velocity, and so there can be about 5% change in the wave velocity, about that 5 to 10%, but not more than that. So that is, so you fix the the toe reflection, you identify and investigate the other part of the wave in the shaft and see what is the integrity of the pile. So that is the time domain analysis. So that will basically, you look at the graph and see whether you can see the defect in there. The other one is actually transient dynamic response method. So that is again, you can see here. So we are using the same hammer, a small hammer, but only difference is that you have a load cell here, and this load cell is actually connected to the data acquisition system. So you can measure the force applied through the hammer blow, and so just like a normal PIT, we measure the pile top velocity as well, and that is also collected here. So only difference is that you use a different hammer with a load cell in this particular transient dynamic response method. Now, in this transient dynamic response method, basically we analyze in the frequency domain. So therefore, we measure the force using that the instrumented hammer, and we measure the velocity using the geophone or the accelerometer, and then we actually get the fast Fourier transform of this and convert this into the frequency domain, and also we get the conversion of this velocity into frequency domain, and then we get the ratio between velocity versus force and plot what is called the mobility spectrum of this particular pile. So in the mobility spectrum, what we say is the anomalies in the form of integrity will appear as actually the peaks and troughs of the frequency mobility plot. So that is basically what we do. So we look at this and we say the distance between these, for example, in this case, there's a drop here, peak here, and there's a peak here. So the between this, so we know the frequency between the between these anomalies, and then that is delta f. And so c is the wave velocity you measure from that particular pile. So then you can see the distance between these two anomalies is actually L is given by this particular C over 2 times delta FL. So now, so this is a transient dynamic response method used for a pile in Sri Lanka. You can see now this is the time domain analysis, right? So this basically will give you the time domain velocity variation like normal PIT. And so in addition to that, you get actually the force measurement of the hammer, and then you convert that into the frequency spectrum and identify this as actually your toe reflection, right? So these two corresponding to the toe reflection, and so if you put that equation there, actually it will coincide with the length of the pile is equal to 16.0 meters, right? So that is the length of the pile. So basically that is the in this case, so the pile is actually 16 meters long, so that will be coinciding with these two reflection in this particular case. And so the other importance of this particular transient response method, dynamic response method, is the initial what you call the dynamic stiffness of the pile. So dynamic stiffness of the pile is actually the gradient of this particular initial low frequency portion, because now this is a frequency axis. So therefore this is a low frequency domain, right? Low frequency area. So here we get the slope of this line as the dynamic stiffness of the pile. And in 1974, Davis and Dunn actually they said that this stiffness, dynamic stiffness, is equal to the stiffness that you measure from the static load testing. So that is of course we did some research in that area, and we made a publication in the European conference as well. So in that we found that this can be applied only for defective piles. So we can identify the defective piles using this particular transient dynamic response method. So this is one area that we can actually move forward and see whether we can make use of this method to get the capacity or the some kind of I would say you can do a more capacity analysis based on this particular method, but not fully though, because we are applying a very small hammer blow even in this case. So the small strain method actually has this Advantages: no need to select the piles for testing before installation as CSL. So CSL cross-hole sonic logging, I have not come up yet, but in that case you have to select the piles before installation, and so there's no need to do that here. You can do PIT on any pile, and comparatively very low cost. The cost is fairly low and very quick. You can do few hundred piles per day, and within the limitations mentioned previously, this method can be used to get a very good idea about the quality of a piles at a site. So you can actually, even though there are limitations, but this can be used as the investigation tool in the piles to select for further investigations. So these are some of the main advantages of this particular method. And shortcomings, there are of course limitations, because if the cost is if it is cheap, then there are limitations. But this is a very good tool to identify the defective piles for further investigation. So the shortcomings are, so of course the limitations are in the length. So you cannot test longer piles in this case. So it is sometimes it is difficult to identify the toes, the defects near the pile top as well as the pile toe, because sometimes the wave is actually attenuated as it goes down, so that it will go a small wave to the pile toe, so you will not see the defects there. And also the pile top, you will see that sometimes the input wave, actually input stress wave, can mask the defects in the pile as well, pile top. So this method very difficult to identify minor defects, and also very difficult to identify gradual variation of the cross section. So this can identify actually sudden variation of the cross section like defects, but if the cross section varies gradually, this is not that effective. And so if you look at the sectional view, right, so you can identify the depth of the defect but not where the defect is located. But if you look at the CSL actually can identify the location, and you can target that location in the rectification as well. So these are some of the shortcomings, but with all these shortcomings, this is a very good tool which can be used to identify the piles for further testing. So the next, the CSL cross-hole sonic logging, that is the direct transmission method. So this is I will not go through this because most of you are familiar with that. So we basically lower two probes, right? So one will emit the wave, the other one will receive the wave, right? So you can actually see the time. So until you get until this particular wave travels this particular tube, you will not see any reflection, any response there. And after that, it is a continuous emission of the wave. So therefore, you will see continuous wave that is recorded in the receiver as well. So what we look at is, what is this first arrival time? So if you imagine that there is a defect here, so there is a low quality concrete here, so then the wave will take actually more time to arrive here. Otherwise, if the concrete is good, it can actually arrive faster. So the sudden changes in the quality of concreting actually can be measured here. So that is basically what you call the first arrival time, or the FAT of the wave. So you can actually put all these as you go down, right, with because this will be lowered, and at any level you will see this. So you can actually get what is called the waterfall diagram. So you will get a collection of the waterfall diagram. So that will clearly show where you, at what point you receive the initial wave. right? So the waterfall diagram is a good way to do that. And so in addition to this, uh, the delay in the first arrival time, so there will be delay, or there will be attenuation of the energy of the stress wave as well. So what we do is basically you plot two lines. What one will actually look at the first arrival time. The other one is we'll look at uh, the energy level, and then see where there's a low level of energy. So I will show you that graph. So we look at these two and say whether the file is okay or not, right? So these actually basically these are the tubes. You can see that in this case they are using steel tubes, right? So these are the tubes, and so they are tying it to the interior of the reinforcement cage, right? So the depending on the diameter, you can use actually you can use 3 tubes, 4 tubes, 5 tubes, 6 tubes, like that. So depending on the diameter, you can have more number of tubes. So general rule of the thumb is actually you're about for each 300 millimeter of the diameter, you use uh, one tube, right? So if it is like 2 meter, then you will use actually approximately about 6 tubes, right? So but minimum is about 4 tubes, right? So and so that we do, and we make sure that so the wave will travel actually. So you are lowering the transmitter and the receiver on on these tubes. So there will be there should not be any hindrance or obstruction to the wave propagation. So there should not be any steel or any other reinforcement that is obstructing the direct path between these two tubes, right? So and also sometimes you can get kind of these tubes can be actually at the top of the pile. These can be debonded, so that you can avoid. And also there can be some kind of leaking of water, because you fill this tube with water before you do the testing. And if you do not prevent that water leaking out, then there's a problem, right? So they are actually you can use steel tubes. Now in this case, steel GI pipes, right? Or else you can use PVC access tubes. So these are called access tubes. You can have actually 4 access tubes, 5, 6, or 3 minimum, right? But general recommendation is you have to use 4. Now, if you use 4 axis tubes, right? So this is a defect-free file. You can see that. So this is actually what is called the waterfall diagram. You can see the first arrival time is not, there's no sudden variation in the first arrival time, right? So this basically the first arrival time, the graph, the line, and also this is the energy of the wave received. So even though there are minor variations because of the compliance of the instrument, but otherwise there is no big variation, sudden variation in these two lines, right? In this case, so this is from tube number 1 to 2, and so this 1 to 3 and 1 to 4, and this tube number 2 to 3, 3 to 3, and 2 to 4. So like that, you will have different tubes. Now in this case, you measure actually this is the cutoff level, and above the cutoff level you are not worried, but below the cutoff level there's no defect here, right? Because there's no change in the first arrival time in this case. But if you consider here, for example, in this case, you can see the wave has not recorded in the other in any of the profiles here, right? So this file has actually 40 access tubes, and it was not the return wave is not observed in any of the between tubes 1 to 2, 1 to 3, 1 to 4, 2 to 3, 2 to 4, and 3 to 4. Right? Any of the tubes, it has not been received. So that means there's a defect, in the entire cross section of this particular the pile, right? Now, sometimes, you can have deflection, defects only in one profile. So in this case, between tubes 1 to 2, you have a defect, and also 1 to 3, there's a defect. And so the little bit between 1 to 4. So the defect is actually concentrated only in this area. But if you look at tubes 4 to 2, there's no defect. And if you look at tubes 4 to 3, there's no defect. And if you look at tubes 2 to 3, there's no defect, right? So this basically the defect is concentrated in this area, something like that, right? So this will be actually what we interpret, right? So waterfall diagram, some diagrams are okay, but some diagrams are showing fat delays in this case. But even in this case, these are some of the measurements, right? So you can see at a certain depth, below the ground surface level, there are defects, right? So in this case, but this CSL method, basically you lower the two tubes, right, to two probes. I will show you actually a video of that, right? So let me take the video first. So let me share this particular video. You can see, I hope that you can see the video, right? So now this is actually, now this is the instrument where you can see the two probes are attached here. Two probes are attached here, and they are lifted at the same level using this instrument. And so there are actually data is acquired here on this particular instrument here. Another thing is that these are the access tubes. You can see that there's no need to prepare the pile top here. So that is one advantage. So even you can do the testing without hacking the pile. Okay. So this is the instrument that is connecting these two receiver and transmitter. So let me share the presentation again. So the you can see, I hope, the screen, right? Can you see the screen?
Yes, we are seeing the screen.
Okay. So basically, now coming back to this presentation, so we have the CSL in this case. Basically, the CSL that is the cross-hole sonic logging. So it has some main advantages. So compared to the surface reflection methods, that is PIT or the PDA, right? Its ability to test the pile irrespective of the depth. So you can see the wave is traveling inside the pile, right? between two access tubes. So the length of the pile does not matter. The other one is the independence of the test results from the soil type present along the pile shaft, because the waves are between inside the pile, so the outside soil presence is no longer applicable here. Ability to identify multiple defects along the pile shaft, because now unlike in the surface reflection method, so where you have actually the multiple defects are reflected back the wave, so there's no reflection here, so there's no problem with this multiple defects here. So this can be performed even when the pile head is not accessible, and visual identification of defect, because now in that case you can actually later I will show you that you can do a tomographic analysis and see like whether there's a defect. So you can use the access tubes to the grout if there is any defect as well in this case. So these are some of the main advantages and disadvantages of the method. So there are some disadvantages. For example, debonding of the access tubes. Sometimes there can be some debonding between the access tubes and the concrete. Defects outside the reinforcement cage are not detected, because now these access tubes are actually inside the reinforcement cage, so you can actually investigate only inside the reinforcement cage. So if the soft toe condition is present below the reach of the transmitter or the receiver, it may not detect such defects. So that is because this probe is about 150 millimeters in length. So therefore it will not reach the, sometimes it is centered, the center line of that. So the bottom 75 millimeters are not, something are not scanned, but that will give us an indication about like if there's a defect there at the toe, then before that, it should indicate that. So and sometimes you can get the tubes blocked, so that is a possibility. And also the other problem is that you have to identify the piles before this method is used, because you have to install the access tubes. But that is not the case with the PIT method, right? So this is a very popular among engineers, because this can be used for when there's less number of redundancies of the piles, and with this quality assurance measures. But of course, there are some problems with this method, but overall it is a very useful method. Now I mentioned about the visual identification. Of course, now this is the CSL data, so which I earlier showed. Basically you do the mental or rather you identify the defective regions, but you can actually do that visually using a particular mathematical tool. Now in this case, you can see this is the pile, and at the bottom of the pile there's a problem. This red zone is that, right? So you can see the red zone, you can actually get the effective area at different red zone, different depths, using the what you call the tomographic analysis, right? So what is called the tomographic analysis, right? So you can see that. So this is possible, and so another advantage is that you can actually target the defective region, because exactly where that particular defect is, not unlike in the PIT case. PIT, you know the depth, but you don't know the section, right? At what part of the section the defect is there, but this way you can identify that. So these are the advantages of this method. But sometimes this particular pile, you can see now all these reinforcements are exposed, right? So but PIT did not show that, because the PIT actually the access tubes are inside the reinforcement cage. So outside the reinforcement cage there can be defects which are not detected using the CSL method. So if you are using, for example, this other method that is called TIP, what is called the TIP is actually a thermal integrated profiling method. So they are actually, you embed in concrete the thermal couples, right? So which will measure the temperature variation. So temperature is connected to the rate of hydration. So heat of hydration is related to the amount of concrete present in that particular section. So if the concrete present is less, then basically you will have a defect. So and also it is even though it is inside the reinforcement to a certain extent, but it will actually give the total cross section. So outside the reinforcement cage also is investigated here. And in addition to this, you can actually look at the verticality of the pile, the reinforcement cage or the piles. And also this can be done at the initial stage of the curing of the piles, right? So after 2-3 days you can do that, because the heat of hydration will not last for a long time, right? So therefore you can actually do this at initial stage of the curing process. So these are the advantages, but we do not have used this particular method, but this is a very useful method that can be used for the assessment of the integrity of the piles. And so this method is about about 250,000 to about 300,000 per pile. But for large diameter piles, we can attain very good accuracy by doing this what is called thermal profiling method, right? So this method is not used in Sri Lanka, not yet, right? But it is actually identified in the STM. So there's a STM standard for this, and you can identify the defects using this TIP, that is thermal integrity profiling method. So this is basically what I want to talk about the integrity testing. So let me go to the other section, that is part 2, that is the load testing. So let me so in this case basically now I am looking at the load testing part. So basically so let me okay, go to the top at the beginning. So basically load testing of the piles, right? So therefore, like we are actually, there are many ways you can test the piles. You can test the pull out capacity, you can test the lateral capacity, you can test the compression capacity, vertical. So in this case we look at only the compression load testing, right? So we apply the load vertically downwards into the pile. So there are different methods of doing this. One is the static load testing. We do, right? So we were doing this one before, and so we can actually do the conventional static load testing, or we can do what you call instrument. You can instrument the pile with the strain gauges and telltales, and then test the piles, right? So then those actually you carry out a static load testing of a pile which is instrumented. So that is basically, these are the two tests, or else you can do a static load testing using Osterberg cell. So in this Osterberg cell, I am not going to explain here, but actually you apply the load from the bottom, from the bottom of the pile, you apply the load vertically upwards. But in the normal case, in the normal static load testing, conventional one, we apply the load from the top. So these are basically, in this particular session, I will talk about only the conventional load testing, but not the Osterberg cell testing. The other one is the dynamic load testing, right? So, commonly referred to as PDA, right? Dynamic load testing. And so the other one is what is called statognomic load testing. We have not done it here, but we may have to do it in the future as well, right? So some of the testing that we are describing here in this presentation are the PDA testing and conventional static load testing and instrumented static load testing, right? So in the normal static load testing, what we do is we apply about 1.5 times the working load to establish the load settlement behavior. So in that case, in general, we do not reach the ultimate capacity, right? So we look at the performance of the pile against, against the settlement limits that are given. And so the important part of this is basically we do not consider the negative sign friction, but according to the Euro code, right? So I have given here the relevant Euro code. So here it says that you have to actually apply the working load plus twice the down drag force. That is the negative skin friction. So if there are negative skin frictions applied on the pile, so if you think that there's a negative skin friction, that has to be considered in the test load. But generally we don't do that. We have to consider that. So we consider only the working load from the superstructure. But if there are down drag forces, then we have to add that to the working load, and test load should be based on 1.5 times the the load applied on the pile. So that is actually the Euro code recommendation. So according to that, we have to use twice the down drag force as well. So if I talk about the conventional static load testing, so there are two testing here. That is, you apply the maintain load testing. That is, you increase the load increment and keep it there, and you measure the settlement with time, right? And then you increase it to the next loading increment. So that is called the traditional maintain load testing. And the other one is what is called constant rate of penetration, CRP test. So in this case, we will actually penetrate the pile at a constant rate, about 1.5 millimeters per hour, or maybe 3 millimeters per hour, right? So like that, we will penetrate constantly at a constant rate and then measure the resistance developed, right? So we can do either way, but in Sri Lanka, what we do is mainly the maintain load testing, right? So just like I mentioned before, we apply the load, and then generally you increase by about 25% of the working load, up to about 1.5 times the or twice the working load. If it is a test pile, you go up to twice the working load. Otherwise, for a normal pile, you load up to 1.5 times the working load. So there's a time limitation for the application of the load, or before that, if you achieve this particular penetration, then you can actually stop and go to the next increment, right? So you can see now this is a test, test setup, and so this is a center beam, and you can see so in the interior you have this kind of you measure the load applied, and there's a hydraulic jack here. Basically, these are hydraulic jacks, right? So the jacking will actually can be applied against the reaction load here, right? And similar load will be applied on the pile, and you can measure the settlement through this particular LVDT, right? So there are 4 of them, and those are actually connected to the computer, right? So you can you can see now this messy event, and so you have to have a special foundation for this loading platform, and these are huge weights, and so you have to stack them properly, and this will take long time, as well as the long space as well. So what you get is actually the load settlement curve like this. So you increase up to working load, and then unload it fully, and then you increase 1.5 times the working load and unload that fully. So there are limitations. So basically, you produce only the load settlement curve and no information regarding the skin friction, end bearing, and distribution of skin friction, and the end bearing magnitude is not given, and no information regarding the integrity of the pile, because now if the pile is okay, if can transmit the load, it will do that, and you don't get any kind of an interpretation, basically integrity of the pile as well. And no information, and relatively costly and time consuming, right? But you can actually, if you instrument the pile, you can get actually a good distribution of the skin friction and end bearing as well, right? So what you do is you look at this settlement measurement, right? So these are the limits given, that is under the working load, it should not settle more than this, and when fully unloaded, it should not, the settlement should be less than this, and at the test load and fully unloading from the test load. So these are the limits that you have to stick to in this particular conventional static load testing. And if you look at the instrumented pile load testing, you can see the piles are actually instrumented with this kind of strain gauges, and strain gauges are distributed over the entire length of the pile. So where you want to measure the load, axial load, and then you can estimate the skin friction. So now these are the actually, in this case, at a given level, there are 4 strain gauges put there, strain gauges are attached. Now, and also in addition to the strain gauges, you get these what you call telltales, right? So in this case, there are 3 telltales. Telltales are actually small diameter steel tubes, right? Steel rods, right? Connected to the bottom of the bottom, and wherever you want to measure the displacement, because these strain gauges will measure only the strains, right? So this is an arrangement of the pile which is instrumented, and basically instruments are attached to this kind of the reinforcement cage, and that is lowered and concrete. So this is basically, it is a traditional static load test that we do, but the pile is instrumented, right? So these are an instrumented pile load testing that is being done. So you can see the instruments are actually, the wires are coming out here from the strain gauges at different levels, and then you carry out a normal static load testing, but you measure the strains at different levels, right, using this, and from that you can get the skin friction at different levels, and of course the end bearing, because you put the strain gauges so that you can measure the end bearing as well. So these are some of this one of the test instrumented load test files. So in this case, about 30,000 kilonewton was applied, and this is a normal load settlement curve. And you can see now here, in this case, actually there are 1, 2, 3, 4, 5, only 5 levels of strain gauges. And so when the load is applied, right? So how the axial force varied along the pile using these 5 strain gauges, right? So in this case, now how basically the instrumentation was done mainly in the rock socket, and you can see the rock socket here will actually mobilize about 1,200 kilopascal, and here about 6,000 kilopascal, something like the lowest value is about 400 kilopascal, right? So that is a kind of the skin friction that is in the rock socket in fairly good rock conditions, but of course these values are fairly accurate, because these are measured developed skin friction. Now, so if you look at the commonly used dynamic load testing, right? So in Sri Lanka we commonly refer to as PDA, but remember that PDA is actually only one such testing. So there are actually two more companies worldwide producing these high strain dynamic load testing, and PDA is actually the USA version of the high strain dynamic load testing. So we are using that, and so that is the trade name, right? So in this case, I will say basically these are the companies that will produce this equipment, right? So PDI is the one that we are using, that is PDA, right? TNO, that is in Netherlands, and Simbat in France, right? But the PDI method is widely used in Sri Lanka, so we refer it as PDA. Right. In this case, you have a large hammer, right? So so depending on I will, and in the next slide I will mention the weight of the hammer. And so the instrument, it is instrumented using accelerometers and the strain gauges. So generally the accelerometers and strain gauges are actually diametrically opposite. The strains are the accelerometer. This accelerometer, you can see the accelerometer actually, if you integrate with time, if you can get the velocity, right? And also you can get the displacement. Now this is a strain gauge, right? So you can measure the strain and you can multiply it by the elastic modulus and the pile cross section area, and you can get the force develop at this particular section. So all these four strain gauges and the accelerometers are actually in one section, you can see, and diametrically opposite generally, right? So depending on the diameter, you can use either 4 or 6 or any number of the strain gauges and accelerometers, but generally they are kept diametrically opposite, right? So this is the actual arrangement, and you can see now all these strain gauges and accelerometers are connected to the data acquisition system, right? So this again a surface reflection method, because while dropping this particular hammer, you can see there's a stress wave, a large one will propagate through the pile and will come back to the pile top here, and then what you measure is basically the particle velocity with time that you measure, right? So that is not located here, that is actually stored in this particular data acquisition system. So generally the instrumentation that you put the accelerometer and the strain gauges about 1 to 1.5 below the top of the pile. So minimum of 2 pairs of accelerometers and strain gauges must be used. For large diameters, preferably 2 or more pairs of accelerometers and strain gauges are used, right? And should not located these strain gauges and accelerometers close to any part of the pile where variation of the impedance exists. So impedance is actually AE divided by the wave velocity, right? So the weight of the hammer should be at least 1 to 2% of the required capacity. 1 to 2% of the required capacity is the basically the hammer weight, right? A relatively thin cushion is typically about 50 to 100 millimeters placed at the pile top. So usually an initial small impact is applied for checking of the instrumentation or that are fixed on the piles, as well as the coordination between the crew. So generally you increase the hammer blows, right? The height you increase, you use the same hammer but increase the height until you reach the stress reach close to the strength limit of the pile. Otherwise, you will not exceed that. So you have to be mindful about that. And also, either we achieve this one, or when the capacity is reached, you can stop the testing. So basically, so the, in the plot, right? So we measure what is called multiplying. So we define what is called impedance. Impedance is A. A is the cross sectional area. E is the elastic modulus of the pile material, and C is the wave velocity. It varies between 3,400 to 4,500 or 4,300 meters per second. So this is a dimensionless quantity. So what you do is actually you multiply the measured velocity at the top of the pile using this Z, right? And then you multiply the force by the Z, and you plot them using with the variation with the time, right? So you do the analysis using the case. There are two methods of analysis. That you do the case method analysis. That is basically you use the case method in the field, right? And then you download the obtained data to the data acquisition, basically to a computer, and do the CAPEP analysis, right? So what is done here is basically in the field is the case method, and this is a more accurate way of getting the results. So what you sometimes, when you get the CAPEP, the file report, so initial values that were mentioned may be changed, right? So first I will talk about the case method, and then go to the CAPEP method, right? So the first one is the case method. So here basically we measure the force, right? So that is the dotted line, and UZ is the velocity multiplied by the impedance, right? So you get the these two graphs. So these are actually the average graphs that you measure, right? So we use actually 2 accelerometers, or rather 4 accelerometers and 4 strain gauges, right? Minimum, right? So therefore, this is the average force variation with the time. You can see this is the time axis, and this is basically the velocity. You measure the acceleration, you integrate with the time, and you obtain the velocity, right? Velocity u, and multiply it by the impedance, right? So then you plot that variation with the time, and you get these two graphs. That is the force variation with the time and the UZ variation with the time. So these are the only two measurements that you make during the dynamic load testing. So these are actually average values that you get from the accelerometers and the strain gauges, right? So the basically in the field, so you are using the case method in the field, right? So the PD operator in the field may use the case method with the assumed value of the case damping factor, JC. So here, so generally we use about 0.5, but in some cases it can be 0.2, 0.3 or 0.4. So we don't know exactly, but he will assume it JC to be equal to 0.5. And also the wave velocity, generally it can vary between 3,400 to 4,300 or 4,500, but he will assume something like 3,500 meters per second. So those are basically the case method values are based on these assumptions, right? So basically, generally this JC value is assumed as 0.5 and C value is assumed as 3,500. So with those two assumptions, you can actually get the in the field. Also, you can get this mobilized skin friction along the pile shaft. You can get the mobilized toe resistance along the pile, develop in the mobilized in the pile toe. The impedance variation along the pile shaft, right? Develop maximum compressive and tensile stresses in the pile shaft, and so on, and also the integrity of the pile shaft, right? So those values that are given are actually subject to these two assumptions. So there are different methods of getting the capacity of the pile. So this is the general equation that we use, right? So this this T1 is actually any time, that is if you T1, and T2 is T1 plus 2L over C. 2L is L is the length of the pile, right? C is the wave velocity that you assume, right? So between this, what basically you get the RMX capacity and RSP and RAU capacity and so on. So depending on the way that you consider, so you will consider the time T1 and always have the time T2 at 2L over C away, right? So you vary T1 around this particular peak value, and then your T2 value will actually vary along that. So based on that, you get the different values of capacities, right? So RMX is actually, you will have the maximum capacity, right? So you will vary this T1 and T1 and coincident intern at T2, right? So you vary along this until you get the maximum capacity, right? So that is basically the maximum capacity here given by this equation. So F1 is actually section where the time is T1. So you measure the force F1 here and U1 here, right? And at time T2, so this is F2 and this is U2. And so JC value you assume, right, 0.5, 0.4 or whatever, and then you calculate the capacity and then you vary T1 and T2, right, so that you get the maximum capacity, right? So that is the RMX method. And RSP is actually, if you consider the first peak only, the peak of first peak, and then you have the T2 at T1 plus 2L over C time away, right? So that is your RSP method. So therefore, basically those are, you can see the depend on the JC value and also on the wave velocity that you assume, right? So so this is a screen that is shown basically to the PD operator, right? So you can see RMX here, right? So we say RMX is if you assume JC is equal to 0.5, we say RMX 5, and if you assume JC is equal to 0.4, RX 4. So like that, you can vary this the assumed values, right? And also you get the RMX, and then in addition to this, these are important ones. What is the compressive stress, CSX, that you measure, right? And the tensile stress that you measure, right? And the other one is basically what is the beta value here. So in this case, it is 100%. Beta is basically the change in the cross section, I would say, right? Change the cross section. So there's no change in the cross section with respect to the normal cross section. So in this case, it is about more than 100%. So this the screen shown by the screen seen by the operator, and you can see the acceleration here on this graph, time acceleration graph, and the time velocity graph. And you can see some one accelerometer is not working. So in that case, it can be a problem with the fixing of the instrument, or else blow is not perfectly applied. So you can actually disable that and then see, right? So these values will be based on that. So this in addition to this, so if you want more accurate results, you can actually do that analysis in the field using the case method, or you can actually do what is called CAPEP analysis, right? So in the CAPEP analysis, you basically what you are doing is you are actually using the wave equation method and signal matching also, right? So in this case, if I go to the next slide, you can see the pile is actually discretized into some number of elements. Each element is connected with the dashpot and a spring, sliding spring, right? So you discretize this, and what you do is actually initially you prepare this model, and you can see at the toe also is connected with a spring and a dashboard, right? So that is a toe spring and a dashboard, and these actually along the shaft, the dashboards, and the along the shaft, the springs, right? So initially you don't know these values in any of these, and what you do is you will assume them, right? So you will assume these parameters, right? What you call the damping ratio, and the damping ratio of the skin friction, and damping ratio of the toe at the toe, and the quake of the toe, along the shaft, and quake of the toe. So you will make this assumption, and then you will consider the equilibrium of these each of these uh, basically each of these elements, moment equilibrium, right? So the motion equilibrium of each of these elements, and then you can actually, based on these assumed values, so you will make an assumption. So basically based on these assumptions, you can actually predict, this model can predict the for example, say you will excite this particular model using the measured velocity, and you can measure actually, so variation of the measured velocity with the time, and you can actually, from the model, you can calculate the force with the time, right? So you measure, you compare the predicted force with the measured force, and then you determine what is called a match quality, right? So you can determine actually a parameter called match quality. So you change this. So if the match quality is not acceptable, so you will change the initial parameters, and then do the matching again. So and then you carry out this process so that the match quality is acceptable, and the predicted parameter, predicted say force, is equal to the or equal to within certain limits to the measured force, right? So you do this particular mapping, matching, and what is found is actually, if the initial parameters are very close to the real values, the convergence will happen very fast. Otherwise, the convergence will be not that quickly attained. So therefore, there's a subroutine in the software itself. So it will assume initial values based on the material that the profile of the soil profile at that location, and then it will do the matching, for the signal matching, right? So it will prepare the model, and also assume the parameters based on the material input, and then prepare the model, and then you input the velocity, and then you predict the force, right? So then you compare the predicted force with the measured force. So now these parameters, you can say that they depend on the soil, but also they depend on the rate of the loading as well, because from the same side, very close to each, the two piles very close to each other, we have seen that the material parameters we assume are quite different, right? So they depend on the rate of loading as well, not only on the soil type. So this kind of the matching, so you can see the initial matching like this. So so in this case, you are matched actually the wave up measured, and you are submitting actually wave up computed, right? So you are matching this whatever the parameter, instead of the force, you are matching the wave up, right? So wave up measured and the computed, right, or the predicted. So this is the initial parameter that you input, assume, and this is the initial match. And you can see here, you can see now if the match quality is not good, then you go back and change the initial assumption, and the matching is better. And you can see finally it has come to the measured is almost equal to the computed, and you can see it is actually kind of a good match, right? So if the match quality is sufficient here, you will stop the map, changing and give this as the result, right? So these are the results in the CAPEP analysis. You can see the in the CAPEP method, you can actually force measured versus force computed, right? So that is measured is given there, right? Using the CAPEP simulation, you get the force measured, and so basically this is a force measured and velocity measured. So these are the measured quantities, right? So this is the section of the pile that is predicted by the CAPEP model, and this is the skin friction variation predicted by the by CAPEP, and this is the load settlement curve that is predicted by the CAPEP, right? So now in this particular site, you can see now these two elements are actually in the bedrock, and you can see that the capacity is about 122 kilopascal, right? The skin friction, and 152 kilopascal skin friction in those two elements, right? And so this is actually the end bearing, the mobilized end bearing. Now, if you compare these values with the measured values in the good rock in the instrumental pile load test, you can see those values are much higher than this, right? So generally the load settlement curves are fairly good. So there's a good matching between the load settlement curves obtained from the static load test and the dynamic load testing, but the distribution can be problematic. For example, now without change the match quality, you can actually put some of these into the skin friction, still you can get the reasonable match quality. So therefore this matching is even though you get the skin friction distribution, that distribution is not 100% correct, right? So it can actually depend on the depending on the user. For example, person who does the matching, it can be different. So this is the match quality that is that you achieve, right? And these are the measured deflection, measured settlement, and the computed settlement, right? So these are some of the other parameters that we use, right? So high strength dynamic load testing. So this will give indirect information regarding the skin friction distribution on the pile shaft, right? At the time of the testing, and also mobilize end bearing, and also you can get the structural integrity of the pile, right? And also you can get the static load settlement curve of the pile, right? So, but since the static behavior of the pile is estimated from the dynamic loading, the accuracy of the results of the dynamic load test depends on the accuracy of the data gathered, experience of the person analyzing the data, and data analyzing model used, right? So these are some of the main parameters, but there can be other factors influencing this, right? So the basically, like you can change the skin friction distribution slightly and then get the acceptable match quality. So sometimes the basically the person who does the matching will have should be very experienced about this. So regarding the final remarks, now integrated testing of piles, right? PIT is an cost-effective way of identifying the defects in the defective piles, and can be can classify for further testing. So interpretation of PIT becomes very challenging and sometimes may be inconclusive in some cases. PIT gives an overall view of the integrity of the pile, right? More research should be done on using IPIT means instrumented pile integrity testing, right? So some research has been done, but more research should be done on this area, because we are not using the instrumental pile integrity testing, but we are using actually the time domain analysis that we use. But a very valuable tool to identify the piles for further investigation, right? So CSL eliminate most of the shortcomings in the PIT And there are some disadvantages of CSL, but the advantages outweigh the disadvantages, right? The possibility of using TIP should be investigated. TIP means thermal integrity profiling should be investigated, and especially for defect-free high-capacity piles are needed. If those are needed, then we may have to go for this kind of TIP, that is the thermal integrity profile. So when it comes to load testing of piles, MLT is a direct way of getting the behavior of a pile and will be used in the future as well, right? IMLT test gives a true picture of the mobilization of the end bearing and friction. So more IMLT should be carried out to develop guidelines for the behavior of rock supported piles, because in Sri Lanka we are blessed with relatively shallow bedrock and strong bedrock in that case. So we may have to make use of that. So PDA testing has many advantages compared to MLT, but not a direct way of measuring the behavior of pile, right? But we have seen that it is a good way of getting the results. But if you know the limitations, you can do good analysis, good picture about the tested piles using PDA. More comparison of PDA test and static load test should be done. Then only we can actually develop further literature on this. Look into the feasibility of doing other types of tests, such as statinomic load testing, because this statinomic load testing has not been done in Sri Lanka. So we may, in most of the other countries, they are using statinomic load testing. So we may have to go in the future for this statinomic load testing. That's all I have to say. Thank you. Thank you very much.
Thank you, Saman. Now the forum is open for discussion. You can raise any questions you have. There are some questions in the chat box. You can raise hand and ask the questions.
Atula, there's a question here that says a cost-wise, which is cheapest, CSL or TIP?
Yeah, there are some questions in the chat box, Saman. Then if you can maybe answer that, then that will be
okay.
fine.
Now, actually, in this case, for example, TIP is costlier than CSL, but it is it will actually avoid some of the difficulties or the shortcomings of CSL. Maybe a good way of getting high capacity piles. So even though the cost is higher, but we can make sure that the piles are actually better quality piles from the TIP testing, because it will measure the integrity much better. The other one is in one software, in one file there is a software, but as per PDA capacity, okay, can this be acceptable? Generally, we load test the piles only up to 1.5 times the pile capacity. So as far as the PDA testing is concerned, if you have actually, if it is satisfactory, if the settlement is satisfactory up to 1.5 times the loading, so at the time of loading, it may be okay, but you have to look at basically what will happen with time. So if you can ensure that nothing will happen with time, and the piles will satisfy the long-term performance, then maybe okay, I think. The other one is what is the recommended match quality? What is the recommended match quality? Basically, the match quality, if it is less than about 5, then we say it is acceptable match quality. But there's no recommended value, but the recommendation is should be less than 5, right? It doesn't mean that you have to have match quality of 3. It is not possible with some of the test results. And so the lower the match quality, it is a better match. But sometimes you will not be able to attain a lower match quality for a given for some of the testing. So the next question is from Kasun. It says, is it possible to calculate skin friction in bearing relative stiffness from PIT test? I think the PIT test, we should not go beyond the limits, right? So we are in the PIT test, we can see we apply a very small hammer blow, right? So if you apply a small hammer blow, sometimes if you can interpret you may be able to get some idea, right? So according to what the example I showed, the 3 piles according to PIT showed different same behavior, but when it was tested using PDA, they showed actually the 1 pile was satisfactory compared to the other 2 piles. So we should not read too much into it, into the PIT to as far as the capacity is concerned, but that can be a tool which can give us some idea about the capacity. But I don't think that we should look into get the capacity from the PIT testing. How can we estimate? The next question is how can we estimate the ultimate pile capacity from the high strain dynamic load testing? So basically, in the static load testing, what you can measure is basically the mobilization of the capacity up to the maximum load you apply. So same rule will be valid for the PD as well. So whatever the maximum load that you apply, then you can actually get the capacity. But if you want to get the ultimate capacity, then sometimes you may have to go for a larger hammer weight, or maybe the height of drop of the hammer will be very large, right? So like that, in that case, but you have to go for a larger hammer weight and also a larger height of drop. But if you cannot increase the height of drop indefinitely, because in that case there will be some problems regarding the alignment of the top of the pile, right? Alignment of the drop as well. So therefore there's a limit, but you can, if you want, you can get the ultimate capacity if you can increase the hammer weight and the height of drop. So there are all those CSL tubes are bound inside the reinforcement cage. Since CSL test is 3D test, why outside the reinforcement cage is not scanned? Because it is not a CSL is not a you scan between tubes, between access tubes. So therefore, you cannot. It is not a 3-dimensional testing. It is a 3-dimensional testing, but inside the reinforcement cage, inside the access tubes, right? So you are not testing outside the access tube. Can the settlement of a pile be 0 in PDA test? Very difficult to get a 0 capacity from the PDA testing because there will be some settlement if you apply a certain load. So getting 0 settlement is very quite unlikely. Can't be totally eliminate the static load test by doing PDA. How do we select the better pile load test? Now, actually, sometimes, if you want to check the actual behavior, you may have to do the static load testing, because there you apply the load and see. It's a direct measurement, right? And so if you do a PDA, of course, it was proven that it will produce the actual the behavior of the pile. It will simulate that, right? So, but if you want to see the real behavior in the real load application, you may have to do the static load testing. But it was actually shown through the research that the PDA can be used for most of the piles. And how do we select the better pile test load test? It is in my opinion, the better pile load test is instrumental pile load testing, right? But in that case, it is costly. But if you test the large number of piles using PDA, then there's a higher possibility, in my view, that you can get a better view about the behavior of the piles in a given site. Atula, there are a large number of questions.
Maybe you may select a few appropriate ones. I mean, you may not be able to answer everything, but go through and select maybe 3 or 4 most appropriate ones.
If PIT test fails in some piles, interrupt foundation. Now this good one. I think if PIT test fail in some piles, is raft foundation is a good solution. It depends on the number of piles that fail, right? What the raft will do is basically raft foundation will distribute the load, right, among the piles. So maybe part of the raft also take the soil pressure, right, and distribute the load as well. So it may be a solution, but of course it will depend on the scenario. The next one is, I think, how can we consider a pile classed as AB acceptable without further testing? It depends on the testing results of the other piles in the site. So if it is a good pile AB, AB means that the toe, the reflection, the stress wave has not penetrated into the toe. So it does not mean that the pile is defective, but you may have to look at the other ways of getting that information, because the consumption of the concrete, the actual concrete to the theoretical ratio, and what is the sub-ground condition of the site. So they may be the other things will actually give some indication, but AB is not the class AB pile is not a defective pile as such. It cannot be defective. I'm sorry that I will not be able to answer all these questions. Right?
Yeah, yes, that's true. That's true. So we select 1 or 2 and we will finish in about 5 minutes time.
Okay. There's a good one, I think. Are there possible situations for inaccurate PIT due to uneven concrete hack surface? As long as the data can be gathered, right? So it is good enough. You can fix the geophone or the accelerometer. Then I don't see a problem. But the hammer blow should be perfectly applicable, right? Should be able to apply the hammer blow, firmly. Otherwise, if you have some weak concrete, then the hammer blow cannot be firmly applied. So in that case, it can cause problems. But as long as It is not needed to have the smoother surface as long as it is hacked properly and the surface is prepared properly, right? To that. So the last one, I answer here like as CSL tubes are installed in the reinforcement before the pile construction, the piling contractor may do better job on that pile. So it will not be a good representative pile. Any technique used to overcome this type of situation? I think maybe you can see CSL tubes. The contractor knows that the CSL tubes are installed and it will be tested using CSL in those piles. But in combination, you can specify, for example, PIT or other methods and see whether there are other piles are also there are problems in the other piles. Like for example, one or two piles can be subjected to Cori, right? Some selected piles can be subjected to PIT, and so on. So you can accept those CSL CSL tested piles. You can test you can use the other methods and see whether those method the entire site the piles are satisfactory.
Right.
Yeah.
So then with that we'll conclude. So I express my sincere gratitude to Professor Thilakasiri for this very comprehensive presentation where many aspects of the pile testing was covered, and to all the members of the audience for active participation and raising good questions to enhance the presentation. Now, this presentation we will be uploading to the website of the Sri Lankan Geotechnical Society. Currently, it is going through a reconstruction process. Within about 2-3 weeks, we will be able to complete that. Once that is completed, this presentation will be uploaded to the as this video presentation. We have recorded it, so it will be uploaded to the SLGS website. So you can read through that or listen to that again. And also, now there are certain questions that we could not answer. In the website, we will keep a forum for you to post questions, and from time to time, panel of experts, I mean, in this case, Samantha Thilakasiri, and in other cases, any other presenter can provide answers through the SLGS website. So we will, with these questions, we will make it a point to create such a discussion forum through the SLGS website. So again, then I will conclude expressing my sincere gratitude to Professor Samantha Thilakasiri for the excellent presentation, and thanking all of you, all the participants, for your interest, and wish you good luck and good night. Thank you.
Thank you.